Vanakkam. Welcome to this course on biomedical instrumentation. We were looking at temperature measurement. In the previous couple of videos, we looked at various ways of temperature measurement. In the previous video, we looked at thermocouples. In this video, we will look at thermometer and using thermistors to measure temperature. And what are the advantages of using thermistors over thermocouples? What are the biomedical applications of thermistors, and what are some of the upcoming methods to measure temperature without contact, non-contact temperature measurement? By the way, not too long ago, this was a hot topic, measurement of temperature of a person without contacting that person. I had to remind you of that period, COVID-19 period, during which you cannot go near a person, but you still want to know the temperature of that person. Right, if the person is having fever or not. So, you use non-contact temperature measurement or radiation based methods. Now, that is also an up and coming, that is already in vogue, but can still be improved. Thermistors are essentially specific materials, special materials. These are essentially oxides of certain metals like manganese, cobalt and nickel that have a specific property. We discussed this in one of the previous classes. In one of the previous videos, a specific property of these materials is that they have negative temperature coefficient of resistance. That is, the resistance of the thermistor reduces with an increase in temperature. That is very much unlike metals. What happens in a metal? When you heat a metal, what happens to the resistance of that metal? Say, take a cable, measure its resistance and heat the same cable and measure its resistance. Will these two be the same? Find out for your own learning. So, these specific materials essentially show a negative temperature coefficient of resistance, essentially this relation, that where R naught is the resistance at some reference temperature T naught. Immediately it becomes obvious that this is a nonlinear function. Is it not? B is a material constant which we can measure and identify, but this has an exponential, that means this is a non-linear function. So, that means that there is a need to linearize this within the range of interest. Typically, a thermistor probe contains the thermistor material, the bead of thermistor material that is sealed inside a glass tube, and its function, the glass tube helps to protect the bead and ensures that the response time is relatively fast. So, this is the, for example, this is the thermistor bead and this is the hypodermic needle that is used to pierce the skin. This is the thermistor bead inside and there is a glass coating outside, and here is a thermistor bead and there is a catheter. So, it is a really small thermistor bead. The sensitivity is about 4% change in resistance for 1 degree Celsius change in temperature. It is a relatively high sensitivity, very, very high sensitivity. Thermistors are usually having high resistance. So, the resistances of the connecting leads, the cables that you use to connect themselves do not have a great influence on the temperature measurement or the resistance change. So, no need to have compensating leads in thermistors. Another concern is that time constant can be high or can be relatively high in thermistors. They can be reduced by reducing the mass of the thermistor. If you reduce the mass of the thermistor, then the speed with which you could measure, how quickly you can make measurements is relatively high. And thermistors can be produced in various shapes and sizes, making them suitable for all kinds of biomedical applications. They can be really small, can be catheter tipped, can be used within a hypodermic needle and all. They can be relatively small as head of a pin, and can be mounted on a catheter tip or a hypodermic needle, and because thermistors are available over a relatively large range of resistance values, it is useful it is quite convenient to match them in electric circuits of interest. Thermistors are available in various physical forms and shapes, geometries, and suit different clinical applications. So, for example, they are available as wafers that are designed to be applied on the skin surface. They are quite ideal for non-invasive temperature measurement, outside temperature measurement. For example, you are interested in measuring the temperature of a baby inside an incubator, for example. They can be used, they can be shaped like a rod, a small rod that can be used to measure rectal temperature, oral temperature, or esophageal temperature. Remember, our interest is to measure core temperature. Remember that. But you are measuring temperature at the surface. You are interested in measuring core temperature. Remember that. Never forget this. These can be miniature beads, really small beads, and they can provide relatively accurate, reliable measures of temperature from inside the body. They can be extremely small and can be mounted on a hypodermic needle and direct insertion into tissues, and if you are inserting it into the body, for example rectal or esophageal probes, these are usually encased in stainless steel sheath. Why? Because we have to ensure biocompatibility, otherwise there will be biofouling, there will be problems by which the measuring system will affect the body or the body will affect the measuring system, both of this, and the accurate internal measurements. Stainless steel also provides the durability that it brings. Another approach is to use resistance thermometer. In this case, the temperature dependence of resistance of some metals are used to use them as temperature detectors. So, in this case, the temperature of a conductor at a particular temperature, or the resistance of a conductor at a particular temperature, capital T, is given by this equation. If I know the resistance at 0 degree Celsius, then I can essentially compute this using some temperature coefficient of resistivity or some alpha, right. Quite frequently these are the metals that are used are platinum and nickel for resistance thermometry, because they can be obtained relatively pure form and are also quite stable. Platinum is a noble metal, for example. The coefficient of resistivity for platinum is actually so small, 0.004 degree, 0.004 ohm per ohm degree Celsius, which is quite small. Means it's going to have very good accuracy. The other approach is to use non-contact temperature measurement using infrared method or using the principle of black body radiation. All objects emit electromagnetic radiation based on the temperature. So, when a person is there, different parts of the body are at different temperatures. Inflamed parts of the body have more temperature within the same person. An ideal black body completely absorbs and re-emits all incident radiation, producing a particular characteristic spectrum. What are the laws that govern this principle? Of course, one is the Wien's displacement law. This essentially relates the emission wavelength, the peak emission wavelength lambda max of a black body to the absolute temperature, where B is a constant which we know. As temperature rises, lambda max shifts to smaller and smaller, or lower and lower, or shorter and shorter wavelengths. What are the other laws that govern this kind of measurement? We already mentioned this, Planck's law and Stefan Boltzmann's law. Please do check what this is. This is beyond the scope of this course to discuss the physics of this. With this, we come to the end of this video. In this video, we looked at various ways of measuring temperature. In this video alone, we looked at thermistors and the advantages of thermistors over thermocouples, and medical application of thermistors, biomedical this, and how to measure temperature using non-contact approaches or radiation based approaches. With this, we end this video. Thank you for your attention.